Welcome, science explorers. Today we're unlocking the secrets of Earth's ever-changing surface with plate tectonics. It may feel like the ground beneath us is solid and unmoving, but in reality, massive plates are slowly shifting, shaping mountains, causing earthquakes, and even forming new land. But what's driving this movement? The answer lies deep inside our planet, where convection currents are constantly at work. In this lesson, we'll uncover how the Earth's layers interact, explore the different types of plate boundaries, and see how these powerful forces shape the world around us. Get ready, because science is about to move you. Earth's surface may seem solid and unchanging, but beneath our feet, massive plates are slowly moving. This movement is caused by convection currents within the mantle, which circulate heat and drive plate tectonics. But how does this work? Before we dive into the details, let's explore how heat moves through materials. This will help us understand how the mantle's convection currents drive plate motion. When materials are heated, they become less dense and rise. As they cool, they become denser and sink. This process, called a convection current, occurs in liquids and gases, but did you know that something similar happens inside the Earth? The mantle, though solid, behaves like a slow-moving fluid over long periods. The heating and cooling of rock in the mantle create convection cycles which push and pull the lithospheric plates above. Deep inside the Earth's core, immense heat is constantly being generated from radioactive decay and residual heat from the planet's formation. This heat energy moves outward, warming the surrounding mantle. But instead of staying in one place, this heat sets the mantle into motion. How does this happen? Hot rock near the core expands, becomes less dense, and begins to rise toward the surface. Cooler rock near the surface contracts, becomes denser, and sinks back down. This continuous cycle of rising and sinking rock is what drives convection currents in the mantle, slowly pushing and pulling the tectonic plates above. The Earth's crust is not a single solid piece. It's broken into huge slabs called tectonic plates. These plates float on the semi-fluid mantle and are in constant motion due to convection currents beneath them. What's happening? Convection currents in the mantle act like a slow-moving conveyor belt, shifting the plates. At divergent boundaries, like the mid-Atlantic ridge, plates move apart, creating new crust. At convergent boundaries, plates collide, forming mountains or trenches. At transform boundaries, plates slide past each other, causing earthquakes, like the San Andreas Fault. Earth's rocks are always changing. The rock cycle is driven by plate tectonics. As plates move, they create, destroy, and transform rocks through powerful earth processes. Magma formation and volcanic rock. At subduction zones, one plate sinks beneath another, melting into magma. This magma rises to the surface, forming volcanoes and creating igneous rocks when it cools. Metamorphic rocks under pressure. As plates collide, rocks deep in the crust experience intense heat and pressure, forming metamorphic rocks. Example: the Himalayas are made of rock that was once at the ocean floor. Sedimentary rock from erosion plate movement causes mountains to rise, where wind and water erode rock into sediments. Over time, layers compact and cement together, forming sedimentary rocks like sandstone or limestone. How convection affects the surface. Where convection currents rise, divergent boundaries form, creating mid-ocean ridges and new crust. Where convection currents sink, subduction zones form, recycling crust back into the mantle. This process leads to earthquakes, volcanic activity, and mountain formation over millions of years.
Use your knowledge of Earth science and Earth science reference tables to answer the questions below. The movement of the tectonic plates is inferred by many scientists to be driven by A. Tidal motions in the hydrosphere, B. Density distances in the troposphere, C. Convection currents in the asthenosphere, or D, solidification in the lithosphere. All right, so hydrosphere is the ocean, so no, that's not it. Troposphere is in the atmosphere, in the air, so then no, it's not that. So we have convection currents. That's what drives it, and that's asthenosphere. Okay, not solid stuff for the lithosphere. Yay! The diagram below shows some features of Earth's crust and the upper mantle. All right, so here's the upper mantle, Earth's crust, whatever. Which model most accurately shows the movement arrows associated with the surface features shown in the diagram above? All right, so these both go up and they move things apart from each other. But this, I don't see anything over here. All right, so it's not this one. Wait, this, that doesn't work like that. They have to rise at the same time. So it can't be 3, and it can't be 2, because these aren't going in the same way. So it could be 4 or 1. And what we have happening here is in the mid-Atlantic ridge, it's divergent, not convergent. So this is our mid-ocean ridge here, and number 1 is our correct answer. Boink. According to tectonic plate maps, New York State is presently located at a convergent plate boundary, above a mantle hotspot, above a mid-oceanic ridge, or near the center of a large plate. Well, we look at our Earth Science Reference Table, page 5, and you will learn that it is near the center of a large plate. Which coastal area is most likely to experience a severe earthquake? The east coast of North America, the east coast of Australia, the west coast of Africa, or the west coast of South America? Well, I think I know this one. It's the west coast of South America. If you're looking at Earth Science Reference Table, page 5, you'll see the plate boundaries along the west coast of South America. The map below shows the northern section of the boundary between the Arabian plate and the African plate. Arrows show the relative direction of the plate motion. So this is a transform. Which of the tape is located at the joint? Well, it's going side by side. So using our key on Earth Science Reference Table, page 5, you learn that this is a transform boundary. Bam! Which of the following locations is the site of a convergent plate boundary? The Mid-Atlantic Ridge is divergent. The Aleutian Trench, the Atlantic Indian Ridge, is divergent, and the Pacific North American plate is transformed. So the Aleutian Trench is our correct answer. Once again, this is on page 5 of your Science Reference Table. Which tectonic feature is associated with complex or uncertain plate boundaries? So we have to look at our Earth Science Reference Table, page 5, to find out where the complex or uncertain plate boundaries are. And that is East African Rift. Base your answers to questions 8 and 9 on the block diagram below, which shows the boundary between two tectonic plates. Which type of plate boundary is shown? We have ocean crust being subducted under continental crust, so they are heading towards each other, or they are convergent. Base your answers to questions 8 and 9 on the block diagram below, which shows the boundary between two tectonic plates. Which tectonic boundary is best represented by this diagram? All right, so we have convergent with the continental crust. So we're looking at maybe this is the Cascade Mountains, and this is the Pacific Ocean, and we look up here where they converge together, and we get the Juan de Fuca plate and North American boundary plate. Here's the magma chamber with the volcanic mountains. Here's the ocean crust going under the continental crust. Base your answer to question 10 through 12 on the cross section below, which shows the major surface features of Earth along 25 degrees south latitude between 75 degrees west and 15 degrees east longitude. Points A, B, and C represent locations on the Earth's crust. So this is A is a location on the Pacific Ocean. This is South America. This is the Atlantic. Here's B, and there's C. Identify the crustal feature located at point A. Well, this is a deep hole, so it's like a trench in the ocean. Ooh, a trench, subduction zone, convergent boundaries. So these are converging against each other, and this trench is formed. Identify the tectonic plate motion that is causing an increase in the distance between South America and Africa. So here's Africa, and here is South America, and the tectonic plate motion would be divergent, or they're separating here at the mid-oceanic ridge. Divergence, seafloor spreading. Bedrock samples were taken at the mid-ocean ridge and points B and C on the grid. Draw a line to show the relative age of bedrock samples between these locations. So relative age, old to new. So you would start up at B, maybe somewhere in the middle, and it would get younger until you got all the way down here where it's just so young, it's just fresh and lava's pouring everywhere, and then it would go right back up. So it looks something like a U or a V. Boink! All right. There's always rocks older, so you wouldn't go, I don't know, if you start at the top. And these rocks coming out are brand new, so you might go all the way down to the bottom. The cross-section below represents a pattern of magnetic field reversal preserved in igneous bedrock of the oceanic crust east of Mid-Atlantic Ridge. Complete the diagram above by shading the pattern of normal polarity on the west side of the ridge center, assuming that the rate of plate movement has constant on both sides of the ridge center. Your answer must be show the correct width and placement of each normal polarity section. All right, so what you would do is you would make this dark band, normal polarity, you would make it just as big as that side, and then you'd color it with a pencil, right? And then you'd make next to that a little square with the reverse polarity, and you'd go dot, 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 dot. Then you'd make a little rectangle with the normal polarity. Then you make a large rectangle with the reverse polarity, dot, dot, dot. And then when you got to 40, you would make this size over here with the normal dark polarity. So it would look just like the mirror image of this side. See, here's a little skinny one, and there's a little skinny one, and then that's there, and that's there. It looks so nice. That's what you would do. And that's the end of the slideshow.